In this video, we'll talk about entity relationship model, which is kind of the foundation of data modeling. It's not just used for creating relational schema, but also useful for NoSQL databases, because it helps you to realize how your data is related to each other, regardless of what database you use to store them. Some of you may already know ER modeling. It's covered in CS4222, the database class, and it's covered in one of the special topic classes, CS4540. In fact, if you just took CS4540 with me in the summer, you'll find that this lecture is almost identical to the one in the summer. It's a good thing that we are doing asynchronous instruction, meaning that if you already know this stuff, you can skip the video and just quickly browse the lecture notes. I do recommend that you at least have a quick look at the lecture notes, even if you already know ER. The reason is that there are many variations of ER, both in terms of notation and in terms of what's allowed and not allowed in attributes and relationships, which in turn affect how they are converted to relational schema. So please at least browse through the lecture notes and make sure you know the notations and terminology this class uses. So as always, the first question is, why do we need ER? ER helps us to design relational database schema. But you may be thinking, what's so difficult about relational schema? It's just some tables, and how hard could it be to come up with some tables? Well, it could be pretty hard. The example I usually use is this. Suppose a friend of yours wants to open a restaurant, after the pandemic, of course. The friend comes to you and says, I'd like you to design the database for my restaurant. However, I don't know anything about databases or computers, so I can't give you requirements like what tables or columns I need. What I can give you is a receipt I got from another restaurant, and I want you to design a system that can print out a receipt just like this. So now you look at the receipt and you ask yourself, how can I turn this into tables? In the real world, some problems naturally map to tables, but many problems don't, and this is where ER modeling can help. Entity relationship model can be thought of as an intermediate step between a real-world problem and a relational schema design. ER modeling takes an object-oriented approach, which is easier to use to model the world than using tables directly. It also provides a set of simple rules, so once you have an ER design, it's easy to convert it into relational tables. An ER design is usually expressed in a diagram called ER diagram. Let's see an example. Suppose we want to design a database to store some information about students, departments, and classes. For students, we need to store ID, name, and address. For departments, ID and name, and for classes, the ID of the class, the name of the class, for example, CS5220, the term of the class, for example, Fall 2020, and the section number of the class, because there could be multiple sections of a class in a semester. We also want to store which classes are offered by which departments and the students enrolled in each class. If we create an ER design for this problem, this is what the ER diagram would look like. There are three important things in an ER diagram or an ER design. Entity sets, shown as rectangles in the diagram, attributes, shown as ovals, and relationships, shown as diamond shapes. Entity set is similar to a class in an object-oriented language. Notice that it's called entity set. An entity would be like an object in an OO language. Attributes are the properties of an entity set. They are similar to fields or properties of a class in an OO language, with a big exception. Attributes in ER can only have simple values like numbers and strings. They cannot be a collection or they cannot be a composite type. There's a simple reason for this. Attributes will later become columns in a relational table, and columns in a table can only hold simple values like numbers and strings. A key is an attribute or a set of attributes combined together that uniquely identifies an entity in an entity set. An entity set must have a key. If there are multiple keys, choose one of them as the primary key. As we can see here, each entity set has an ID attribute. The ID attribute can uniquely identify an entity. It is underlined to indicate that it is the primary key of the entity set. Note that the entity set can have more than one key. For example, student names are probably not unique, but department names are. So the name attribute of a department is also a key. Also for sections, the combination of name, term, and section number can uniquely identify a section, so it is also a key. And then we have the relationships, which are the tricky part of ER. There are three types of relationships: many-to-many, many-to-one, / one-to-many, and one-to-one. If each entity in one entity set can be related to many entities in the other entity set, and if each entity in the other entity set can be related to many entities in this entity set, the relationship is called a many-to-many relationship. Remember, the most important thing when you try to determine the relationship type is to check both directions. Take one entity on one side and check the other side, and then do it again the other way around. If each entity in one entity set can only be related to one entity in the other entity set, but each entity in the other entity set can be related to many in this entity set, is called a many-to-one or one-to-many relationship. Many-to-one and one-to-many are the same type of relationship. It just depends on which direction you look. For example, if we look from entity set 1 to entity set 2, we can see that it's many-to-one. But if we look from E2 to E1, we can see that it's one-to-many. Again, when you try to determine relationship type, check both directions. And of course, if each entity from one entity set can only be related to one entity in the other set, it's a one-to-one relationship. Now, knowing the relationship types, let's try these relationships as examples. So, one student can take many classes. One class can have many students. This makes this relationship a many-to-many relationship. Again, notice that if you only check one direction, for example, if you only check student and classes and didn't check the second one, it may seem like this is a one-to-many relationship, but if you check both directions, you'll know that it's many-to-many. How about departments and classes? One department can offer many classes, and one class can only be offered by one department. Let me shrink the fonts a little bit. And this, of course, makes this is one-to-many / many-to-one relationship. And how about person and favorite movie? By the definition of favorite, each person can only have one favorite movie. And again, if we stop just here, we may be thinking that this is a one-to-one relationship, but remember to check the other direction. One movie can be the favorite of many people. So this again makes this relationship a one-to-many / many-to-one relationship. Now, in our version of ER diagram, we use an arrow to indicate the one side in a relationship. For students and classes, no arrow. For departments and classes, the arrow is on the department side, as the departments is a one side in a many-to-one, one-to-many relationship. In the favorite movies relationship, the arrow is on movies because it's a one side in in this relationship. Note that arrow here has nothing to do with direction. It's just a way to indicate the one side in a many-to-one, one-to-many relationship. Some other ER notations shows a number 1 on one side and the letter M or N on the other side. Something looks like this. And on the many side, it will say either M or N. It's the same thing. So we are just using an arrow to indicating one without using numbers or letters. Don't confuse the arrow with direction. It's just representing the one side. ER modeling is a way of modeling data. When people first learn ER, they usually find entity sets easy to understand because they are just like classes, and you can kind of visualize data in an entity set, like Joe, Amy, Tom in students entity set, and CS 1222, CS 3220, and so on in a sections entity set. What people don't realize right away is that relationship also contains data. For example, the take relationship between students and sections contains data that tells us which student is taking which class. As we'll see later, entity sets will become tables in a relational schema. Relationships will also become parts of a relational schema. Some relationships, like this take relationship, will become a table, and some relationships will become columns in other tables. So now that we know the basics of ER model and ER diagram, we can try it out with this example. Note that knowing the syntax of ER is just like knowing the syntax of a programming language. It tells you the basic rules, but you still need to figure out how to use it. So let's say we want to design a database for a company to keep track of their employees and projects. Each employee has an ID, first name, last name, and date hired. Each project has a leader and a number of members who are also employees. The first thing we do is to identify the entity sets, attributes, and relationships. There are no simple rules that you can just blindly follow to come up with a design. There are some rules of thumb those you can use to come up with a reasonable design quickly, and then you can revise and refine it. So here are some tips. When you look at the problem description, norms tend to be entity sets and attributes. and the verbs tend to be relationships. If a noun can be stored as a simple value, like first name, it's likely an attribute. And if a noun contains multiple values, like an employee has a first name, a last name, and a date hired, it's probably an entity set. By the way, we consider date and time as simple values, just like numbers and strings, because they can also be stored in a single column in a relational database. Another important thing to consider is that when you have something that looks like an attribute, but it is of an entity type or a collection type, then it must be a relationship, because remember, attributes can only have simple values. Example here would be the project leader and members. They seem to be attributes of a project, but because a leader is an employee and members are a collection of employees, they must be relationships. This is different from an object-oriented programming language, where you can have them as class fields or properties. So after the first step, this is what we have. Note that there are two relationships between employees and projects. One relationship, employee leads project, and the other relationship, employee participates in projects. It's not uncommon to have multiple relationships between two entity sets. The common problem after this step are basically trying to make relationships into attributes. Again, remember, attributes cannot be of entity type or collection type. And also don't try to create ER design like a relational design by using something like a leader ID. There's no foreign key in ER. If two entity sets are related, there should be a relationship. The second step is to determine the relationship types. So here we have one employee can lead many projects, and one project is only led by one employee. So it's a many-to-one, one-to-many relationship, and the employee is the one side. For the other relationship, one employee can participate in many projects, and one project can have many employees. So this one is many-to-many, no arrow on either side. And then we put on the finishing touches. Make sure each entity set has a primary key that's underlined in the ER diagram. Add some attributes if necessary. Remember, your clients may not be computer science people. They may not give you detailed instructions on exactly what information they need you to store. Oftentimes, you need to fill out the details yourself. In this case, even though the problem description doesn't mention project ID or name, it probably makes sense to add them. Now that we covered the basic cases of ER design, we need to look at a few special cases. The first special case is when an entity set has a relationship with itself. Take this one, for example. Suppose each employee has a supervisor, and the supervisor, of course, is also an employee. So how do we model this? You may want to add supervisor as an attribute, but we know it's wrong because supervisor is of employee type. You may try to put employee ID as an attribute of employee, but it would be also wrong because we are doing an ER design, not relational design, and there's no foreign key in ER design. The correct way to model this is to use a relationship. This relationship is between employees and itself. Just like any relationship, we can determine the relationship type. One employee has one supervisor, and one supervisor can supervise many employees. So this is a many-to-one, one-to-many relationship. To distinguish the supervisor side and the employee side, we label the edges, and these labels are called rows, and we put the arrow on the one side. Another special case is something like this. Suppose we have two entity sets, players and teams. Players have two attributes, name and jersey number, and teams have one attribute, name. Team names are unique, so team name can be used as a key. But player names are not unique, and jersey numbers are not unique either. So what's the key for players? You may be thinking that if we combine player name and jersey number, it may be unique. But consider that there may be a player, for example, Johnson, with jersey number 10 on the team Lakers, and another player, Johnson, with jersey number 10 on the team Celtics. So even the combination of name and jersey number may not be unique enough. In this case, players is called a weak entity set, meaning that the entity set doesn't have the attributes to form a key. In order to have a key, it must borrow the keys from one or more related entity sets. In this example, players must borrow the key from the team's entity set. By combining the team name and jersey number, we can now uniquely identify a player. In ER diagram, weak entity sets are drawn with a double border, and the relationships from which it borrows keys are also drawn with a double border. Another special case in ER is a subclass. It's kind of like a subclass in an OO programming language. In ER, there are no methods involved, only attributes. If you want to inherit the attributes from an entity set and also want to add some additional attributes, you can create a subclass. There's a special relationship. It's a relationship between the superclass and the subclass. The relationship is drawn as a triangle in ER diagram, and is a, of course, means a student is a user. Generally speaking, it's a good idea to actually avoid using subclasses in ER because they tend to make your design more complicated without providing much benefit. Here are a few examples. For both B and C, administrators and regular users, and pop songs and country songs, you are likely better off just using one entity set and an attribute like user type or genre to distinguish the entities. For beer and wine, most people consider them so different that you should probably just use two different entity sets for them. The only case here that probably makes sense to use subclass is salaried employees and hourly employees. These two types of employees share quite some attributes, but also have quite some attributes different, so it makes sense to use subclass here. So now we know ER. Let's see how we can convert an ER design to a relational design. Remember, ER design is just an intermediate step. In the end, we need to store our data in a relational database. Converting an ER design to relational is basically about converting entity sets and relationships to tables. Converting an entity set, as you would imagine, is pretty straightforward. So entity set name becomes table name, attributes becomes columns, and the entity set key becomes table key, and that's it. Converting relationships is a bit more involved, and different types of relationships become different things in relational design. A many-to-many relationship becomes a table that contains the key attributes from the associated entity sets. A many-to-one relationship becomes a foreign key column on the many side, referencing the one side. For example, in this offer relationship, the relationship becomes a department ID column in the classes table. And the classes table is a many side in the relationship. This column is a foreign key column referencing the ID of the departments table, which is the one side in the relationship. Regarding foreign key, know that it's a concept in relational design. There's no foreign key in ER design because it's a relationship in ER. In a relational model, a foreign key represents a connection between two tables, and in SQL, it's used as a data integrity constraint, meaning that the database system will check if a value in a foreign key column is a value in the key column it references. So here are the steps to convert an ER design to a relational design. First, convert the entity sets, then the relationships, and then you can rename some tables and columns so the names make more sense in a relational schema. Let's use the company database as an example and see how it's done. The first step is easy. Just take the entity sets and make them tables. So here we have two entity sets, employees and projects. So two tables with ID, date hired, first name, last name, 4 columns, and ID name, 2 columns. We then convert the relationships. Participate is a many-to-many relationship, means it becomes a table, and the columns in the table are keys from the associated entity sets, so the ID from employees and the ID from projects. So this is a table converted from the participate relationship. Lead is a many-to-one, one-to-many relationships. So it becomes a foreign key on the many side, which is projects. And the foreign key references the key of the one side, employees. So a foreign key column on the many side referencing the one side. And then we put in the finishing touches, mainly to make the tables and column names more natural or more descriptive. For example, I would change the table name from participate to project members, and probably also change employee's ID to leader ID to show that this employee ID is the ID of the project leader. So how do we convert one-to-one relationship? Well, one-to-one relationship can be considered as a special case of one-to-many, many-to-one relationship. It becomes a foreign key column, and the foreign key column can be put in either table. With that said, although it's technically correct to put the foreign key column in either table, usually it makes more sense to have it in one table than the other. For example, here we have a one-to-one relationship. One faculty can chair one department, and one department only has one faculty as its chair. We can convert the relationship into tables in two ways. We can have the foreign key column in the faculty table, or we can have it in the departments table. Although both are technically correct, in practice you'll see that having it in departments table would be better, because if we have it in the faculty table, we'll notice that this column will have lots of nulls because most faculty are not department chairs. Converting a relationship with rows follows the same rules as before. The only difference is that for a one-to-many, many-to-one relationship like this, both the one side and the many side are the same table. So in this case, again, we follow our steps. First, converting the entity set, we'll have a table called employees with ID and name. And then we convert the supervised relationship. This is a one-to-many, many-to-one relationship, so it becomes a foreign key column on the many side. The many side, of course, is employees table, so it has a it becomes a foreign key column on the many side. And this foreign key column references the key of the one side, which happens to be also the same table. And here are the rules to convert weak entity sets. It basically says add the keys of the supporting entity set to the weak entity set, and the supporting relationship doesn't need to be converted. What that means is, again, let's start by converting the entity sets. So we'll have players with player name and the jersey number. And teams with team name and location. And we'll add the key of the supporting entity to the weak entity set, which means we are going to add this one to here, so we'll call it team name. And the supporting relationship doesn't need to be converted. So this ER design becomes just these two tables. Converting subclasses to tables is a bit tricky, which is, by the way, another good reason to avoid using them in the first place. But if you do have subclasses, there are 3 different ways to convert them, resulting in 3 different relational schemas. In different contexts, these 3 different approaches have different names. Here we'll call them the object-oriented approach, the ER approach, and the Null approach. In an object-oriented programming language, a subclass has all the inherited properties of the superclass plus its own properties. This approach is called the OO approach because the table for the subclass is like a subclass in an O language. It has all the inherited attributes plus its own attributes. This approach is called the ER approach because it looks just like the ER diagram. Notice that in the ER diagram, the shared attributes are in the superclass ID name, and same here. The shared attributes are in the superclass table users, and then in the ER diagram, the subclass, the attributes of the subclass is attached to the subclass, and here again, the additional attributes of the subclass is in the subclass table. Note that the difference here is that the subclass table must also now have a foreign key column, because the data for the subclass entities, like Jane here, are split in two tables. We need a foreign key to connect them back together. The last approach is called the Null Approach, which is basically putting everything in a big table. Because some records don't have certain attributes, like a regular user doesn't have a CIN, there will be lots of nulls in the table. Thus the name, the Null Approach. A typical Null Approach will also use an additional column, often called a discriminator column or discriminator field. This column stores the type of the entities in the class hierarchy, like student for students and staff for regular users. Without this additional column, if we want to, for example, select all the staff users from the table, we'll have to check if the CIN is null. That is not a reliable way to get data, especially if you have more than one subclass. There are multiple factors to consider when you choose which approach to use to convert ER subclasses. Generally speaking, if query performance is your biggest concern, which is often the case, you should use the Null Approach. You can try the following 3 queries using 3 different approaches and see what queries you end up with. You'll find that you only need to do single table selection for all 3 queries with the Null Approach, but you'll need to do join or union with the other 2 approaches. As an exercise, design a database that helps people to keep track of the characters and their relationships in Game of Thrones, shown in this figure. First, do a ER design and then convert it into tables. So, have fun and see you in the next video.